Okay, we've got two more things to look at with evaluating limits algebraically. The first is evaluating limits algebraically where, say, x approaches c, a certain value. And the second part is as x approaches infinity. So you might see as x approaches infinity. We may not get to that in this video, but we'll see how far we get. We're going to start first with an algebra review. So I have a rational expression, 3x squared plus 5x plus 2 over the quantity x minus 4, x squared minus 4, and I'd like us to factor those two expressions. So the denominator, you might recognize this as the difference of squares, and the difference of squares factors into x minus 2 times x plus 2. Okay, you might recall that these are conjugate factors. So for example, a minus b and a plus b are conjugate factors. And when I multiply conjugate factors, the nice thing about that is that the middle term, the negative ba and the positive ab, cancel out. And so we just get a squared minus b squared. Okay? So this is actually the product of conjugate factors, this difference of squares. Okay, the numerator, 3x squared plus 5x plus 2. Well, let's see. The only way to get a 3x squared would be with a 3x and an x. And the only way to get a 2 is with a 2 and a 1. 5's in the middle, so I'm going to suggest that we put the 2 here. And the 1 here. That would be a 1x and a 6x. No, that won't work. So let's go back. Let's put the 2 here and the 1 here. That will be better. Both need to be positive. Here I'm going to get the 2x. Here I'm going to get the 3x. That'll give me the middle term, 5x. Okay, so we have factored, and there is no reducing happening here, so we're done. Okay, so let's take a look again at some conjugate factors. What if I have the factors the square root of x plus 5 times the square root of x minus 5? Remember, when you multiply conjugate factors, you just get a squared minus b squared. The first thing gets squared. So the square root of x squared is just x, and the last thing squared, which is x squared, x minus 25. Okay. All right, we're going to use that idea of conjugate factors when we want to rationalize the denominator or the numerator. So in this example, we're going to rationalize the denominator. I would like to try to simplify this denominator. It looks a little bit messy with 2 minus the square root of x plus 4. What I'd like to do is multiply by the conjugate of that denominator. All right, and when I multiply, I can only multiply by 1 and not change my expression. So I have to use that conjugate in the numerator and denominator. Now the key is multiply out the conjugates. You're using the conjugates for a reason. So in the denominator, we're going to get 4 minus the product of these two square roots is just going to be x plus 4. Now be careful and make sure you use parentheses in that denominator. Okay, so first piece squared, 2 times 2 is 4. Second piece squared, the square roots multiplied together just give you the radicand, what's underneath the square root, and that is a minus. Okay, the numerator, don't multiply out the numerator. It's not going to give you anything nice when you do multiply it out, so don't bother. But there's another reason why not to bother, and that's because something nice is going to happen once I start simplifying. So the numerator stays in factored form. Or I should say the non-conjugate factors stay in factored form. The conjugate factors, like you see here in the denominator, you're going to multiply out all the time. Okay, when I simplify the product of the conjugate factors, 4 minus the quantity x plus 4, I'm just going to get a negative x. This negative 4 and this positive 4 are going to cancel out. Okay, when all's said and done, look what I have in the numerator. I have an x in the numerator. I have an x in the denominator. Those two factors of x are going to cancel, and I'm going to be left with a negative in the denominator. So I'll just call it negative 1 times 2 plus the square root of x plus 4. Okay, or negative 2 minus the square root of x plus 4. Okay. Next review question. How do we work with complex fractions? You may or may not have learned this method. You may have worked with common denominators, but I want to get to a simplified fraction more quickly and efficiently. And so what I'm going to choose to do is multiply by the LCD over the LCD. So I'm really multiplying by 1. Okay, so if I look at all the denominators in all three of my fractions, x, x minus 1, x minus 1, the least common denominator is x times x minus 1. Okay, I'm going to multiply the numerator by that x times x minus 1. I'm going to multiply the denominator by that. So let me do that. So in the numerator, this x is going to drop out. I'm going to be left with negative 2 times x minus 1. Plus, this x minus 1 is going to drop out. I'm going to be left with 3 times x. I have no more fractions in the numerator. In the denominator, this x minus 1 is going to cancel out. I'm going to be left with x plus 2 times x. Okay, let's do a little simplifying. I'm not going to multiply out the denominator just yet because I want to see if anything drops out. So I'm going to leave that in factored form for the moment. But let's simplify the numerator. So we're going to get negative 2x plus 2, negative 2x plus 2, plus 3x. Simplifying some more, it looks like in the numerator I get x plus 2 over x times x plus 2. Look at that. I have a common factor in the numerator and denominator. I'm going to reduce that and call this 1 over x. So this big, messy, complex fraction is equivalent to 1 over x. Okay. Let's go on and use our properties of limits to evaluate analytically. So this means we got to do some algebra work. Now, the first method is the easiest method. Okay? We are going to use direct substitution. So if you think about what does the function x minus 7 look like, you should know it's a line, right? And as x approaches 5, you know you're just going to plug 5 into that function and figure out what the y value is. Okay, so substitution leads to 5 minus 7, or negative 2. It's just the y value on the function. Okay, the limit of a quadratic. Okay, the quadratic has no special things happening, right? If you want to know what's happening close to 5, plug 5 in. 5 squared minus 3 times 5 plus 2. So 25 minus 15 plus 2. What do we get? 12? Okay, a constant, the constant pi is always 3.14, etc. As x approaches 5, the limit is going to be pi. This is the limit of a constant, is the constant. This is the limit of a difference, which is the difference of the limits. Okay, well, the limit of x is 5, the limit of -7 is -7, you're going to subtract them. Okay, so I'm kind of using the graph in my head, but I'm also saying, hey, just substitute the number. This will always work for any polynomial. All right. Okay, so we did a little bit of factoring and canceling in our algebra review. For each of these rational expressions, we would like to check first to see if we can factor and cancel. So let's take a look at number 18. The limit as x approaches 3, x squared minus x minus 6. How do we factor that? To get a -6, I'm pretty sure I'm going to need a -3 and a +2 because I want that x to be negative. All right, looks like I have factors that cancel. I'm left with the limit as x approaches 3 of x plus 2, which is substitution. Substitute 3 in for x and you're going to get 5. All right, if you remember from your rational function work, this rational equation, its graph, will actually look like the line y equals x plus 2, but it will have a hole in it at 3. So at 3, there's going to be a hole in this graph. Okay, all right, the next function. Oh, look at the denominator, a difference of squares. So I know that factors into conjugate factors, x plus 2 and x minus 2. These guys are going to drop out, but don't forget this x minus 2 is in the denominator. So we're looking at the limit as x approaches -2 of 1 over x minus 2. Substituting, we're going to get 1 over -4. Okay, this rational function has a hole in it at -2, comma, -1/4. Just like this last one had a hole at 3,5. Okay, this last rational function, you might remember your rational functions. It's going to have a vertical asymptote at x equals 3. So it's that 1 over x graph shifted 3 units to the right. Okay, so I want to know what is the limit as x approaches 3. So from the left, the limit is -infinity. From the right, the limit is +infinity. So what are we going to say about this? The left-hand limit does not equal the right-hand limit, and therefore this limit does not exist. Okay, you can take a look at 21 and 22. You're going to need to use the conjugate factors to rationalize the numerators, and we'll come back to that in the next part of Day 2's video.